For most of us, understanding a fish begins with a square and a triangle. These are the basic geometric building blocks we use as children to represent life in the sea. But the theoretical shapes of a classroom are quickly overwhelmed by the chaotic, physical reality of the open ocean. Take the whale shark. It reaches lengths of 18 meters, the equivalent of stacking 12 children end to end to reach from its nose to its tail. This graphic illustrates the biological weight of that scale. We are looking at a 16,000-kilogram organism. Its mass is so significant that it exists in a different mathematical category than the children use to measure it. Navigating a world of this magnitude requires moving beyond basic geometry. For traditional fishing communities, survival depends on the precise, scaling application of mathematics as a primary operating system. Out on the ocean, survival is dictated by the algebraic relationship between three specific variables: the speed of the vessel, the time spent on the water, and the final yield of the catch. The baseline for this equation was established by the traditional logboat. The modern industrial machine trawler operates on an entirely different scale of magnitude. This data dashboard shows the operational limits of the traditional logboat. It moves at a sustainable 4 kilometers per hour, typically yielding a 20-kilogram catch per trip. If we update the chart, the trawler travels at 22 kilometers per hour and hauls in 6,000 kilograms in a single trip. Watch the chart expand when we calculate the yield over 7 trips, 42,000 kilograms, completely engulfing the logboat's contribution. This isn't just a gap in profit, it's an ecological countdown. If machine boats continue to harvest baby fish at this rate, the ocean's regenerative equation eventually zeroes out. Back on land, the macro-logistics of the sea transition into the high-speed environment of the local fish market. Within this crowd, fisherwomen perform constant mental arithmetic to protect their margins before the catch begins to spoil. Consider Fazila. She is carrying an 8-kilogram kingfish, and her target for the entire sale is 1,200 rupees. The arithmetic happens instantly. To find her bargaining floor, she divides that total price by the weight. 1,200 divided by 8 gives her a rate of 150 rupees per kilogram. When these microtransactions scale across the whole country, the numbers grow into lakhs, hundreds of thousands of workers, and crores representing tens of millions of rupees in daily trade. In this environment, profit and loss are decided by fractions. Rapid arithmetic is the primary tool used to ensure daily economic survival. To defend against the volatility of the market, the community built the Meenkar Bank, a cooperative financial system managed entirely by fisherwomen. The foundational math of the bank is straightforward. 20 women contribute 25 rupees each month, creating a collective monthly pool of 500 rupees. This area chart visualizes the outcome of that discipline over a decade. Small, consistent deposits compound into significant capital reserves. This capital provides a self-funded line of credit. Instead of turning to predatory lenders with ruinous rates, she can draw from the cooperative to purchase high-cost essentials, like a 4,000 rupee fishing net. She repays the loan at 345 rupees a month for 1 year. The math ensures she can sustain her household, while the bank earns enough interest to remain solvent for the next member. By saving 74,000 rupees collectively, these women funded their own fish drying factory. They took control of the processing stage, ensuring that even a smaller, sustainable catch could generate the revenue needed to remain independent. Mathematics is rarely a static textbook subject. From simple geometry to the logic of pooled capital, it is the toolkit these women use to secure their economic autonomy in an ocean increasingly dominated by industrial scale.